Thank you. So the reason why I submitted this talk was because I work in networking, and there was a lot of buzz around EBPF, and I didn't know anything about it, and I wanted to force myself to learn it. So the result of this journey is this talk. This is to say that I don't use eBPF in production, and I'm not a kernel programmer, but I hope that this will give us some value. Some quick words about me. I'm Federico. I work for Red Hat. I've been working for Red Hat for almost 5 years now, and I'm this networking team in charge of making the Kubernetes platform suitable for telco applications. And because of that, I contributed to a variety of Kubernetes-related projects, and lately I'm maintaining MetalLB. Is anyone using or know what MetalLB is about? Just, do you like it? Okay. If you found it less stable in the past couple of years, that was because of me. So we can say that in possible different ways that eBPF is now a mature technology. I remember watching a talk by Leonardo in 2019, and things were way more clunky than they are today. We can say that eBPF has crossed the chasm. There are a lot of eBPF-based tools that are available to us. We might be already using it, even if we don't know. And even the development toolchain has reached such a level of maturity that is usable by the majority of us. But what is eBPF? Does anyone knows what eBPF is? Who is building stuff with eBPF? Anyone? Okay. Who is an expert? I know that we have at least one in the room. So eBPF stands for Extended Berkeley Packet Filter, which is more or less a legacy name. The marketing hook is that eBPF stands to the kernel as JavaScript was to the browsers, meaning that it allows us to inject some code into the Linux kernel in order to change its behavior, and I will add in a safe and controlled way, which is pretty important. We don't want to mess up with our kernel. Couple of eBPF properties are that eBPF programs can be loaded dynamically, and this is particularly important if you want to change the behavior of your fleet of thousands of servers without having to restart them. And another important thing to remember is that eBPF is event-driven. So any eBPF program will be executed in reaction to something that happens inside the kernel. And, pardon. Okay, so why do we care about eBPF, or what makes eBPF so special? As Go developers, or it depends. The majority of us shouldn't care about using it unless we work in infrastructure. But there are a lot of useful eBPF-based tools that allow us to inspect and to understand how our system runs. So let's have a look at the regular kernel interaction. We have our application, we have the hardware, and we have the kernel that provides some level of abstraction over the hardware. If we want to print out something on the screen, if you want to access to the network interface, then you have to perform this syscall, and a context switch happens. The control goes to the kernel that knows how to interact to the hardware and get back to our application. On the other side, eBPF programs live inside the kernel, specifically inside a virtual machine that is running inside the kernel. So they don't have to pay this context switch that happens in our applications, and at the same time, they are able to interact with the underlying kernel. So one nice field of application is observability. Having something running in the kernel that is able to see what is happening, regardless of the applications that are running, is particularly useful, especially considering the fact that it can observe the system as a whole. So if we have a bunch of applications running in the kernel, we have this centralized point where we can observe what is happening. And This is true also with containers, because containers run on the same kernel, and there is this Kubernetes thing that is running containers all over the place, and having something like that might be useful. Another nice field of application is networking. Again, we have our application, wants to talk with some external server. It has to go through the kernel to send packet to the networking interface and to receive packets. With eBPF, we can put some code that intercept those packets and apply some logic before even those packets reach our application. So we can decide to drop those packets, for example, or to manipulate those packets and send them back, or just to throw them to our application because we want the application to be aware of those. There are, of course, other alternatives to change the behavior of the kernel. One is Linux kernel modules. They are a bit less safe. I'm going to expand this later. And of course, you can even contribute some feature to the kernel. But the kernel has a very high entry bar, and the timing between you want to implement something and the time where that kernel will be available might be long. And this was just a glimpse. I will show more use cases later. So let's have a look at a very easy and simple example and a disclaimer. There will be C code through all the presentation, or a subset of C. The kernel side supports Rust 2. I was supposed to make jokes about the fact that I'm speaking at the GoLab, but this is a kind of a mixed track, so I won't make them. But during this presentation, I will focus on eBPF probes written in C. And this is like the bare minimum hello world related example. For now, it's enough to know that this program will be invoked every time an execv syscall is called in our kernel, and will print something somewhere. In this case, just called. And the way we build it is we take our C program, we compile it, and then it generates some bytecode that gets eventually loaded in the kernel. And what happens is, regardless of who is calling that syscall, our program will be invoked and will print something. So it's pretty powerful. Like it's a dumb example, but should let us understand a bit how powerful this thing is. But at this point, somebody might stop and think, wait a minute, do I really want to be able to run something like this in my kernel? Because like my kernel is, if I make my kernel crash, like it will bring down all the applications running on it. And this one is one of the aspects that I think make eBPF really cool. And first and foremost, the most obvious thing, you need to have the right permissions to load the eBPF programs. You can't load them as a regular user. So you just you either need some capabilities or you must be root. But there is also the eBPF verifier, which is kind of the gatekeeper for the safety of our programs. And again, I already said that we produce our bytecode, and then with this bytecode, we need to load it into the kernel. And in order to do that, there is this BPF syscall that allows us to load the program. And the first thing that gets hit is the verifier. And then if the verifier is happy, most of the time it's not, the program will go through a JIT process, and it will be installed into the kernel. And the verifier checks for a lot of stuff. Infinite loops, memory access out of the permitted bounds, the program size, even if there are techniques to overcome the size, the complexity of the program, if the program is performing some calls that it shouldn't because they don't belong to that particular program type. And this is probably the biggest hurdle when somebody starts with messing up with eBPF. The verifier will return some cryptic errors that are hard to triage and to understand. but it's what keeps eBPF safe to run as well. So now let's have a look at the generic structure of an eBPF program. This is like the bare minimum. We will have some maps, the program, and some includes. And I will start dissecting each part of the program. The program itself comes with a sec macro that drives which part of the L file the program is added to, and also kind of refers the type of the program. Then, and this is the sec macro. Then we have this context parameter. The meaning and the type of the context parameter depends on the program type. If it's an XDP program, like in this case, you will find the network, the buffer that contains the network packet, but it depends on the program type. And this is the same for the result. The result, the meaning of the result, so what is going to happen if we return a value or another, depends strictly on the program type. And we said that we have these programs running into the kernel, but despite running in the kernel, they kind of like run into this sandboxed environment, so they can't go around and mess up with any part of the memory of the kernel. So in order to overcome this, there are these utility functions called EBPF helpers that allows us to interact with the context and with the underlying helper. And this is taken from the man page, and this is exactly the definition. These helpers are used by eBPF programs to interact with the system or with the context in which they work. And each program type can call only a subset of these helpers. So for example, if you have an observability-related program, it won't be able to use network-related eBPF helpers, and vice versa. And the verifier will yell at you. This is, again, an example. In this case, I'm using this BPF getCurrentCom. I'm not checking the return error. These are just examples. They might not load at all, or they might contain some errors. But in this case, the getCurrentCom is an helper that let us understand which is the com attribute, which is basically the name of the executable. So if we have some observability program and we want to understand who is calling what, this is something that we might find handy together with a few other helpers. Now, I want to talk a bit about maps, because running these programs in isolation is fine, but we want to drive more or less their behavior. So maps are the bridge between eBPF programs running in the kernel and the user space. They can be read and written by both sides. So by using maps, you are kind of exposing an API to the user space that can configure the behavior of your program accordingly to the use needs. So there are various ways to use maps. They can use to pass configuration. You are interested only to check if a program is accessing a certain folder on the host, or you want to parse packets only coming from a certain network CIDR, for example. This is a configuration that is applied by the user in the user space and gets translated by something that can be read by the eBPF program. They are used to save state and share data between programs. There are some programs that can be attached to entry and exit functions, and a common pattern is to use a map to link what is being observed from the entry point and to the exit point. And they are also used to send data to user space. So if you have something that is processing a lot of events and you want to send them to the user space, there are specific maps that can do that. And once the data is on the user space, you can do whatever you want. You can build a castle on top of that. You can have web UIs and monitors and alerting system on top of that, of those. There are many types of maps. I listed just a few: arrays, hash maps, last recently used. Perform ring buffers are used to send data to the user space. There are even more complex data structures like Bloom filters, maps that are per CPU, and so on. And this is how you define them. You have the map attached to the maps section of the file, and you define the type of the key, and you define the type of the value and the max entries. And this is how you use it on the eBPF side. So you fill them up, and in this case, we take the current command and we fetch the action that we want to perform based on that command. This is just an example to show how to access the map from the eBPF side. And this is another example related to ring buffers. Ring buffers are a circular structure that is quite efficient. And by using this construct, you can reserve some space inside the ring buffer and fill it without having to allocate the memory twice. You fill the event, and then you submit it to user space. So we have eBPF programs, we have maps that are kind of the bridge to the user space. Now I want to talk about portability. Because our programs, or the result of the compilation of our programs, are an artifact that we want to distribute. And ideally, we want to be able to run this program on as many kernels as we want. But that comes with some challenges, because different kernels might have different data layouts. Like, we are developers, we optimize, we change our data structures. So what is true for one kernel might not be exactly the same for another. You move field, you put fields into nested structures, you add the fields in the middle that change the memory layout. And the program is not aware of the memory layout. So the kernel developers did something which is called core, compile once, run everywhere, which is a smart solution to this problem. Before core, the solution was to ship the source file and the build toolchain on every host and rebuild it inside of the host. So in this case, we have the L file, we can move it around and have it run. And how does that work? It's built on top of a few components. BTF is kind of a metadata that describes the program. Every program, if compiled correctly or with the proper compiler and options, has some BTF information associated to it. For example, which fields from which structures it wants to read. And the kernel comes with BTF information too, so it tells where each field is. The loader matches what the program wants to read with what's available in the kernel and provides the program some offsets, so when it looks for a field, it will get the offset and will find the field in the right place. Another thing that I showed in the very beginning was these two includes, and the VM Linux file is basically it's a generated C header file that contains all the kernel structures except the macros, and that is built out of the BTF information related to the kernel. So by running this, you generate a .h file that you can use. For the macros, you can find them in the BPF helpers file. So we are quite in the talk, 20 minutes-ish. And we might wonder, we are at GoLab or at Rust Lab. What does this have to do with Go or with Rust? And the thing is, as I said, every eBPF-based application comes with a kernel side that is written in C or in Rust, and a user space side. And no wonder you can write the user space side in many languages. C is one of them. Go is another, and Rust is another as well. In Go, there are a couple of libraries. One is the Cilium eBPF, which is native Go, a native Go implementation. And there is libBPF Go, which is a wrapper to libBPF, which is C-based. So it comes with all the pain points related to C Go. So in this talk, I'm going to focus on the Cilium eBPF library. And I think this library made an excellent work in consuming and using eBPF in a very efficient and simple way. It removes away a lot of the complexity that was there in the beginning. It comes with this BPF2C to go tool that allows that takes the C code and generates the BPF L file for us. It even embeds the L file inside the generated binary. So we have to move around only one artifact instead of two. And it provides a way to access to the programs and to the maps from the Go side. And it also generates the Go equivalent objects of the C structs. All of this in an automatic fashion. The way you use it is you pass and you give a name to your program. You pass the types that you want to convert from C to Go, the program, of course, and it will generate a bunch of generated code for us. This is how it translates the structures. Instead of having to do those by ourselves, it will do that automatically. Those are the references to all the objects that are generated out of the C. So we get this object container that contains the references to the maps and to the programs. And this is how we access the map. So we have the map from on the C side, and on the Go side, we have the map that is available through this objects variable. We have our arguments that take from the command input or from the desire of the user. And then we can put them into the map or look for parameters. So this is the way you interact with something that is running in the kernel from the user space. Oops, yeah, and this is the reference to our map from the Go side. And also with eBPF Go, we can take our program taken from those objects and attach them to the corresponding hook. We can consume and read from performance and ring buffer, and has some kernel feature discovery in case you need some particular feature from the kernel. So what can we do with eBPF? I'll showcase just a few simple use cases. It's not comprehensive, but just to get a good understanding of all the crazy stuff that we can do. One is kernel inspection. In order to understand what's happening to the kernel, we have a few instruments at our disposal. Some of them are K probes and K red probes, trace points, perf events, and many others. And what are K probes? A K probe is a way to add an hook, an eBPF program to the entry point or the exit point of any kernel function. If your kernel has a function defined, you can attach an eBPF program to it, and this is particularly powerful. Of course, the API is not guaranteed to work on all the kernels, because kernel developers might decide to refactor and change the signature of their functions, but if you attach to syscalls, they are reasonably stable. So in this example, we can have an eBPF probe that checks who is opening a particular file, because you might want to restrict the access or to get notified if something is accessing the passwd file, for example. You want to understand if somebody is behaving in a way that he shouldn't. And the way we do that is to attach the probe, and then we interact with the context structure, with the context parameter, and I said already that depends on the type of the hook. And in this case, we have these macros to fetch the second parameter, which is the path name of the file that is being opened. And by doing that, we can have a good understanding of who is opening what on our whole system. We can do something even more interesting, which is, killing who is opening a given file. And again, here we say we have a map that comes from the user space that tells us the action done depending on the path name. In this case, the key is the path name We look into the map, we check the arguments. If arguments is killed, then we use this. This is a helper that sends a signal to the process. So we can have a blacklist of files, and if our program tries to open it, the kernel will automatically kill it. So it's a nice way to implement security in our system. Another way to inspect our kernel is to use tracepoint. Compared to kprobes, tracepoints are specific hooks into the kernel. The kernel developers thought that those places were interesting to observe and put hooks into the kernel. We have the guarantee, the stability guarantee compared to kprobes, and out of BTF we get generated data structures from the parameters, so we don't have to re-implement them and to parse them. We get them in that vmlinux.h file, and we can get the list of the trace points available in the virtual file system of our kernel. In this case, I tried to look for all the available trace points related to the socket buffer. And in the Linux kernel, you have the definition with a lot of parameters, and this is it will build a trace.something event that you can find into the kernel source. So by doing that, we can check what packets are being dropped. We can have an hook to the free socket buffer trace point, and we get the parameter for free from that include file, and then, we can check the reason for the dropping. We can also inspect user space. We have uprobes and uret probes. They are more or less the same as kprobes. You can attach to any function defined into the user space, so our programs or our dynamic libraries. They must be attached to the specific binary, and of course they offer even less stability guarantee, but they might be useful for well-known libraries. In this example, we intercept SSL write calls in OpenSSL, and this allows us to fetch the buffer passed to SSL write and to read what is being encrypted before it gets encrypted, of course, which is pretty nice. Or not, depends. So yeah, this is the red probe, and I'm showing here the pattern I spoke about before. We have this map shared by the entry point and the exit points. We have the parameters in the entry point. We have the exit point here. We process it in some way, and then we send the event to the user space. Networking. Networking is another part where EBPF is super powerful. It allows us to do a few crazy things like packet filtering or even packet manipulation. We can drop packets. We can intercept those packets, change something, and send them to the user space, or even send back to the network interface. This is how, for example, the Facebook load balancer works. Every call that is done to Facebook goes to this XDP-based load balancer that intercepts those packets, manipulates them, and sends them back to the right destination. XDP stands for Express Data Path, is an eBPF type that intercepts packets very early in the stack, meaning that either when they are just received from the kernel, or even if the card supports it, even directly into the network card. You can do many things with the packet. You can pass it to the kernel, you can drop it, or you can manipulate and redirect it. But it's tricky. You just have this big buffer, and you have to deal with pointers to manipulate that packet. Again, this is a quite simple example. In this case, the context parameter contains the buffer of the packet. We want to make the verifier happy, so we need to check that we need to check the boundaries of our packet, and then we need to check that what we are inspecting falls within those boundaries, because otherwise we won't be even able to load this program. And then I should have done that also for the Ethernet header, but I didn't have much room in this slide. But then after we perform all these checks and we fetch our data, we can perform some business logic. In this case, it's quite simple. I just check for the type of the protocol, and if it's not TCP, I will return drop, which tells the kernel to drop the packet. But we could also do something like redirect and change the source IP and the destination IP and send it to some other host, for example. So it's really, really super powerful. TC is another way to manipulate packets. TC happens, traffic control was meant to do traffic shaping and so on, but it's also used for attaching EBPF programs to the kernel. Allows us to do more or less the same stuff, but it's a bit higher in the kernel. The packet is already in the kernel memory. We have this nice socket buffer form of the packet, and contrarily to XDP, it works for ingress and egress as well. And this is yet another example. In this example, the packet is supposed to go through an interface, but we intercept it and we send it to another interface with a different next hop based on the source IP. So this is what comes from the user space. Based on the source address, we fetch the next hop, which contains some stuff, and we use that stuff to fill the neighbor info, and we use this BPF redirect helper that takes the packet and sends it to another interface. So depending on the use case, for example, it might be useful. The Go side is, as I said, trivial. This is how we attach the program. We use the link package from the EBPF library, and we link our program taken from the objects to the right entry point. And interact with the maps. I already showed some examples. It's easy, but now we are about to leave the land of tutorials and hit the reality. And the reality is not that easy. So making the verifier happy is an art, or at least it was from me as a newcomer to EBPF. So when you miss something, it's painful. You'll get some not easy to understand errors, and these are just some examples. You get references to the registers of the virtual machine. You don't even get the line of the code that is causing that error. So one approach might be like doing some sort of binary search and to comment the code to understand what is causing that. Every program type is a micro framework. They come with different context arguments. They have different meaning of return values. They have different eBPF helpers available. They have different ways to load the program and different life cycle. What might work for networking because you attach the program to the networking interface might not work for observability or security. Even understanding how to parse the parameters, how to parse the context might be challenging. You need to be familiar with the kernel. You want to know what packets are being dropped, but what is the right hook? Do I need to use a trace point? Do I need to use a K-probe? Where is this information? Is it better to monitor a syscall? Maybe there is an eBPF specific program type. Using eBPF is easier to do kernel programming, but it's still kernel programming. There is no debugger. So we have everything, and it's not working. Did we attach the right program? Are we passing the parameters correctly from user space? Are we parsing them correctly from the other side? How about packet manipulation? I already said that you can mess up with the packet, but you have the checksum to regenerate. You have the buffers to be in the right place, and it's hard. And also you have all kernel supports, because in reality, you have legacy. You have all kernels and all that stuff. And it's a lot. But there are some tools that we can use. So how can we debug? Call me old school, but I like to log. And logging is a good way to understand, of course, when you are developing, if your program is running and if it's getting the right parameters and so on. And also there is, if you have BTF enabled, there is this BPF tool that is kind of a Swiss knife that exposes a lot of stuff. You can use it to see what programs are loaded into the kernel. You can even dump them to see that you are the right program, and you get references to the registers. So it might be useful to understand the verifier error, and you can also inspect the maps. So if you want to know if the user space is filling the map correctly, you can inspect it by the command line. You can check for trace points. There are some trace points that are related to eBPF. So you use eBPF to debug eBPF. And there is this BPF trace that allows us to inspect eBPF events in an awk style way. So for example, in this case, I looked for all the XDP-related events, and then I tried to look for the error, and I saw that I was getting these 2 error, which is still obscure, but better than not knowing that. Test in isolation, meaning that like you should start growing your eBPF-based application from a prototype that is self-contained and well isolated. And lastly, don't be afraid to look into the kernel. After all, our stuff is going to run somewhere in the kernel, so there will be likely to be a place where this code is executed. And also, something that we are particularly good at, take inspiration or blatantly copy from existing applications. Now, there is a very active ecosystem of production-ready BPF applications that you can look at. So that is also a good starting point. The last thing I want to talk about is what real projects look like. So I already said that we have this very thin eBPF layer that we attach to our server. We have, it might be Rust, but here it says good. We have this user space side that talks with our application through the map, which is the kind of the API. We combine the two. We don't need to distribute 2 different artifacts because the library is so cool. And then we have this little package, and then we use many of these little packages to give our application eBPF powers, and then our application might live in a wider context with microservices, and then you might interact with Kubernetes and other higher level concepts, and you might want to send the data to a database. This is to say that once you have this tiny layer of eBPF, you will probably build a very big castle on top of that. That is the bridge between your application and the user context. So you might want to relate that network interface to something that is happening inside a Kubernetes pod, so that the user is happy and is able to understand what is configuring. So the user space side is in charge of a lot of stuff, is in charge of the life cycle of our programs, is in charge of how to store these events and to present the data or to do the configuration according to the business use case, and is in charge of passing the parameters to the program. So that's like, eBPF has its challenges, but also the user space side and how you consume it has its complexity as well. Wrapping up, we are almost to the end, and we will be able to go to lunch. You have a kernel side and a user space side. You need to be familiar with the kernel or willing to learn. You can use the maps as an API, and every program is a different type. And eBPF is really powerful. You can do stuff that wasn't possible before, but it's also difficult to tame. I left just a few resources. Another problem with EBPF is that it's kind of ungoogleable because it's a so fast-moving target that what you find over the internet might be already obsolete. But there are some well-known resources. Leeds Rise Learning EBPF book from O'Reilly does an excellent job in bringing you through this path and understanding the big picture that sometimes it's hard to find. EBPF.io and the kernel documentation, and as I already said, if you want to copy some logic, there are plenty of applications. Some are easier to understand, some others are harder to understand, and of course the example section of the Go library has a lot of good examples. And with that, I'm done. If you have any questions, I'll be happy to try to answer.
Sono ancora io. Hi. I wanted to know if there's some established approach for unit/integration testing of a BPF program.
I think there is something, because when I was doing the research, I hit some results, but I'm not sure. So again, I don't use it in production. I just did some prototyping. What I did was just to build something locally and make it work by hammering it.
It works on my machine. Okay.
Yeah.
No, it's
but I think
totally fine.
I think the fact that the technology is now getting mature and used in production, there are probably ways to verify that, and having a look at those projects might be a way to understand if, because they are using it in production, so they either have tests or it's not possible to.
Yeah, thank you.
And of course, one last thing, you can still end-to-end test it. So you have your whole application and observe the behavior.
Hi, thank you for the talk. So on the previous slide, you said that you can run only C in the kernel and Go or whatever language you can run in the user space. Is there a reason that only C in the kernel?
It's C and Rust, actually.
Aha, yeah, makes sense.
No, no, but I think I'm not sure if it was clear, but you can run either C or Rust.
Okay, yeah, thanks.
Yeah, thanks very much for the talk. The verifier, it tries to make sure that the programs are safe to run in the kernel. Is that verifying that it's for sure secure, or it's more heuristics to hopefully make sure it's safe?
No, we should trust it. It was written by kernel developers, making sure that there are a lot of things that the verifier checks in order to make sure that you are not hammering the memory somewhere, for example, or that you are, because if you write in where you shouldn't, then the whole kernel will crash. So.
Thank you for the talk. Are there any signs or best practice that, hey, you should move this part of your application to EBPF side?
I guess there are very specific use cases of EBPF. One is observability/security, and the other one is networking. So they kind of still relate to infrastructure. If you are handling packets, for example, and part of your application is relying on, I don't know, IP tables or IP rules to steer the packets somewhere, maybe BPF is a good alternative. But as I said, it comes with a learning curve and some risks, because you are moving away, it's more efficient, but on the other side, you are moving away from safe ground to something that it's you that is messing up with the memory of the packet and sending it back. So.
I think that's all. Okay, thank you, Federico Paolinelli.